Hello and welcome. We are on our last week and we have gone through a long way, but I felt that the course will remain incomplete without one topic. So far we have talked about amplifiers, lot of different circuits made up of op amp. But you know, op amp is not a very basic element. It is made up of, it is basically an integrated circuit. Okay? So, it is made up of possibly lots of transistors, etc. Rather, a transistor is a more basic element. So, we talked about op amp from its functional behavior. We did not talk about how it is made. That will be difficult to talk about. So, I thought that at least let me give you some flavor how we can do some instrumentation with transistors without using op amps. Okay? So, because transistors are more basic elements than an op amp is. So, we will do some small circuits, will not go too much into the detail, and if you feel it difficult, I promise I will keep it out of the syllabus of the exam. Okay. So, transistor based instrumentation. And I shall use only BJT because this is the transistor that you all might have studied. Okay. So, let us first make a voltmeter with an electronic voltmeter with a BJT. Now, before that, let us recall why we need electronic voltmeters. So, why we need electronic voltmeter? There were two reasons. Number one, if we want to measure small voltage, very small voltage, so that we may need to amplify it, so that the pointer goes towards the rightmost position in on the display on the dial, so that we do not make much error while taking the reading. And second important reason is that if we want to increase the input impedance of the voltmeter circuit to have high input impedance of the voltmeter circuit. Why? Because say if we have a circuit and we want to measure the voltage between say these 2 points A and B, the moment I connect a voltmeter V, this voltmeter will start to draw some current. Practically and ideally, the voltmeter resistance should be high, so that this current is low, but voltmeters do not have infinite impedance. Therefore, this current is not 0. Therefore, some current is coming out of the circuit, which will load the circuit and cause voltage drop because of the internal resistance of this or impedance of the circuit. Okay. So, the internal impedance and this current, their product will give the voltage drop between these two terminals when I connect this voltmeter. Now, okay, say just consider this situation. Okay. So, voltmeter draws current causing voltage drop. So, this is the problem. I'll just show you how we can get rid of this problem using just one BJT, bipolar junction transistor. Okay. So, solution, a very simple solution. Okay. So, what we will do is this, say we will take a BJT, this is an NPN BJT, and we will apply, say, let us take a resistance first. Let me apply the this voltage. Okay. So, I can redraw this circuit A, B, this is the circuit. Okay, and I'll put here a voltmeter, some plus voltage, call it plus VCC. Now, what will happen is this. So, this has some resistance, call it Rm, meter resistance. Okay. And this voltage is VAB, right. Before we analyze the circuit, I think I should very briefly recap the functional behavior of a transistor, recap the functionality of a transistor, of a BJT. Okay. So, BJT is governed by two rules. So, if you know just two rules about a BJT, you pretty much know everything how to analyze a BJT based circuit. So, rule number 1 is, so okay, if I call this as the base, this as the emitter, and this as the collector. Okay. So, it has three terminals, base, emitter, collector. Then the first rule is this plot, this characteristic plot between the voltage VBE versus the current IB, this current IB. Okay. Not necessarily in this circuit, in any circuit. We are talking about a BJT only, not necessarily in this circuit. And we know that this looks like this. Okay. And so, initially no current flows up to some voltage, and after that almost any current can flow without much change in voltage. Okay. So, this is approximately 0.7 volt, and we can, I mean, for sometimes we can approximate these characteristics like this, 0 and then vertical line after 0.7 volt. This is current, base current, and so this is rule number 1, which tells me for what value of VAB how much current will flow through the base. Okay. So, this curve tells me the value of base current as a function of applied voltage between B and E. Now, okay, and this is the approximate rule, which says no current flows up to 0.7 volt and any amount of current can flow after that uh, and the voltage will not increase. This is rule number 1. And rule number 2, this says what is the relationship between IC is the collector current which is entering through the collector, and IB. So the first rule, this was relation between VB and IB, and second rule will talk about the relation between collector current and the base current. And the rule is IC is less than some beta which is a constant times IB. This constant is a property of the BJT. Okay. So the second rule says the approximately the current that can flow through the collector is less than this. So I can say IC maximum value of the IC is therefore beta IB. It can be less than this and it cannot be greater than this because of this rule. Okay. So this is the second rule. Now let me just give you some examples before I come back to this circuit. I'll come back. Before that, so let's take so let me say apply a voltage between this like this. Say, and a voltage between this like this. Okay, for simplicity, I will put the resistance here. For simplicity of calculation, this is the simpler example. Plus, minus, plus, minus. I give you that this resistance is 1 ohm. Okay, this voltage is say 20 volt. This voltage is say 1.7 volt. Okay, this resistance say this is 1 ohm. Now, so solve this circuit. To solve this circuit means I have to find all the voltage and currents. So say IB, this is IC, this is IE, emitter current taking in this direction. Okay. So what are these values first? IB is how much, IC is how much, IE is how much. All these things I'll ask. Okay. Now let's apply a KVL in this loop. Call it loop 1. Okay. So KVL in loop 1 tells me this 1.7 volt. This is the voltage rise from here to here. Then there is a drop minus IB times 1 ohm. Okay. So this is a rise 1.7 minus this drop. Then there will be another voltage drop, call it VBE minus VBE, and then this is a short circuit, so there is no more resistive drop or any drop, so this should be equal to 0, right. Now So from this you can write 1.7 minus, or you can write this is equal to IB into 1. Okay. So if I write IB in ampere, then this will be in volt. So I do not have to write the unit for simplicity of writing. So this will be equal to plus VB. Okay. So you see that IB plus VB is this much. Okay. Now how can we find IB? So what we can do, let's first draw this curve. This is VB versus IB. This relationship comes from the property of the BJT, and this is from the external circuit. This is another relationship between IB and VBE. You see this is here, from this you can write IB is equal to 1.7 minus VBE. So this is a straight line, y equal to minus x plus c. So that will be a line with slope 1. This is IB. Okay, and this intersection point will tell me the value of VBE and the value of IB. Now, what we will do? We will do an approximation. This is a very useful approximation which we always do. Copy paste. Instead of having this curve, we will approximate it like this, vertical and then horizontal. Then this intersection is directly given by the point that VB is equal to 0.7 volt. This is 0.7 volt. This is the approximation I have done, and from this I can get the value of IB. How? So let's put this value here. So I will get 1.7 minus 0.7. So this will come out to be 1 ampere. I have taken the numbers in a way so that the calculation becomes easy, because I do not have a calculator. Okay. So IB comes out to be this. Now suppose it is given that beta is equal to 100 given. Okay. So what can we say about IC? So IC is therefore should be less than IB into beta, which is same as IB is 1 ampere multiplied by 100, which is 100 ampere. It should be less than this. Okay, it cannot be more than this. But will it be equal to this? That will depend on this circuit. Okay. So in this circuit, you see, so from here to here, so let's think about this second loop, loop 2. So here, from here, if I consider this as my reference point, 0 volt, then this voltage is 20 volt. Then from here to here, there is no voltage drop. So this point is again at 0 volt, and from here to here there is this VB is 0.7. So this point is at 0.7 volt. So this point is at 0.7 volt. This point I do not know. So if I call this at this is VC, I do not know the value of VC. Okay, but I can say that the value of VC is 20 volt minus this drop, okay, minus this drop, and minus IC into, let me call this R2, if R2 is 1 ampere 1 ohm, then 20 minus IC into 1. Now if IC is 100 ampere, okay, if IC is 100 ampere, then definitely it's not going to work. I mean, because then Vc is going to be negative. Okay, if IC is equal to 20 ampere, then Vc will be negative, and this is not possible. So what will happen, IC will be much less than 20 ampere in this circuit. Okay, where R2 is equal to 1 ohm. Okay, but say if I modify this, if R2 is equal to 0.1 ohm in the previous circuit, then what can I write from this? I can write Vc is equal to 20 minus IC into 0.1, which means divided by 10. And now IC can be 100, which is the maximum value, because if IC is equal to 100, then Vc will be 20 minus 100 by 10, which will be 10 volt. Okay, so this is fine. So Vc will be at 10 volt, and this point is at 0.7 volt. So that means 9.3 volt will appear at between collector and the base. So VCB will be 9.3 volt. So this is 10 minus 0.7, so on so on, I mean equal to 9.3 volt. This is fine. So this will be the solution. Okay, but in the previous circuit it was not possible. Okay, because Vc was going to a negative value. If 100 ampere flows here, then 100 volt drop. So the current that will flow here is much less. Maybe in this case IC may be equal to around half ampere, or maybe not half, maybe sorry, so maybe around, sorry, not half, maybe around 20 ampere, less than 20 ampere actually, maybe let me just call it maybe 19 ampere. Okay, maybe. Then what will happen if this is 19 ampere? Then this 19 ampere into 1 ohm, there will be 19 volt drop. So if there is a 19 volt drop, then Vc will be 20 minus 19 is, it will be 1 ampere, and maybe this 0.3 ampere will remaining 0.3 ampere will drop across this. Okay. Exactly what will be the value? For that we need another curve which gives me the value of IC as a function of IB and this voltage VC Px or VCE. Okay. So, but I am not going to, so this circuit I am not going to give you the exact answer. Okay, that's going to be, I mean, that going to take more discussion. So, but what I say, the important point I want to say that in this circuit, IC is less than, is strictly less than beta IB, because I mean, we do not have sufficient voltage in this path to have this much current, because voltage drop is becoming very high if I have 100 ampere current. Okay. But here important fact is IC is equal to beta IB in this case. So, this is the rule. I mean, basically, if IB amount of current is flowing here, then beta IB times current at maximum can flow here, and then this current will be IB plus beta IB, which is beta plus 1 IB. That is the maximum current which can flow if I have sufficient voltage drop in this path. Otherwise, current that will flow is much less. So, that is the behavior of a transistor. Now, let us go back to our voltmeter circuit. So, this is our voltmeter circuit. So, I am applying a voltage VAB here. The resistance that is here is Rm, okay, and it will draw definitely some current, because you know, I mean, this point is at a higher potential than this, so it will draw some current, and in the active region, you know, this voltage will be around 0.7 volt, VBE will be around 0.7 volt. Okay. So, therefore, what will happen is this: the voltage that we will have across the meter. So, let me just write the solution, and you please verify whether my solution is correct. Just think yourself. So, I am saying Vm plus minus, this is my reference, will be VAB minus 0.7 volt. This will be the voltage across the meter. The current that will flow in this circuit, or say IB. Now, IB I will write, this is this. Okay, before I can find IB, if this is IB, the current that will flow in this branch, it will be beta IB. It will be, I mean, if it works properly, it will be beta IB. It will not be less than beta IB, because you know there is no resistance here. So, there will be no voltage drop. Okay. So, beta IB will flow through this, and this current therefore, which is IE will be IB plus IC, which will be same as beta plus 1 IB. So, this much current flows here. So, now applying KVL here, I can write VAB is equal to, so VAB, let us take this side positive, this side minus, reference. So, this is voltage rise, then I have a 0.7 volt drop. 0.7, then this drop is plus Rm times IE. So, from this I can write VAB is equal, or VAB minus 0.7, this will be Rm times IE, and IE is nothing but IB multiplied by beta plus 1. Okay, so this is the solution. Okay, this is the solution. Now, how does it help? It helps because you see only the current that is drawn from the circuit is IB, but the current that flows through the meter is 1 plus beta times IB. Okay, current drawn from circuit is equal to IB, but current through the meter is equal to 1 plus beta times IB. Now, this IB is a small number or a smaller number, but this is a bigger number, large number. So, more current is flowing through the meter, which means we can have more deflection, because we know that for any normal meter, more current flows through it, the coil will be deflected more. So, we will get more deflection. So, we will have more deflection because the meter current is more, with less current drawn from the circuit, being measured. So, the voltage drop also in the circuit will be small, because we are drawing small current, low current here. Okay. So, we are drawing low current, so voltage drop will be small, but the deflection of the meter will be high, because the current that is flowing through the meter is high. And you know, the extra current is coming from here. This is IB, and we are getting extra current beta times IB from this source, okay, which is coming to this meter. So, the important point I will say is that extra current is coming from the supply VCC. Okay. So, that is why this is an active measuring, this part is an active measuring instrument. It has its own power source. It is not dependent on the power from the circuit only. It has its own power source. So, this is an active instrument with its own power source. So, it takes less power from the circuit, less current actually, and the remaining more current is supplied from the power source of the measuring instrument only. So, this is the measuring instrument together. Okay. So, this is my measuring instrument. Okay. So, that is the beauty of an active circuit. Okay. So, it will not take current from the circuit being measured. it will take very less current, it will take less current, and large amount of current will be delivered by this voltage source. Okay, so this way, we are drawing little current from the circuit. I am repeating, we are drawing little current from the circuit, and I am essentially getting the current amplified. Okay, not the voltage amplified, but the current amplified. This is like a current amplification, you can say. So this way it helps. So this is important to understand how this circuit helps. This is a simple circuit. I repeat, this is a simple circuit where by virtue of the rule of the transistor, which says the current that will flow through IC is beta times the IB, therefore this current will be more than the current being drawn. Okay, this circuit is called an emitter follower. I do not know exactly why, but I guess this is because, so possibly because, and you can also remember this in this way, possibly because the meter voltage or the voltage that we are measuring, meter voltage is equal to the input voltage V input minus the drop in BE minus the VBE drop. VBE drop. So essentially, in other words, I can say that meter voltage is same as the emitter voltage. Maybe that is why it is called an emitter follower. I am not very sure. Okay, but this is how you can remember. Essentially, we have this, that the voltage that appears across the meter is same as the emitter voltage, which is same as the input voltage minus 0.7 volt. Now let us ask some question. Okay, so question, some numerical problem. Say in this circuit, I draw it again. So the voltage is applied here, V in plus minus. If so, the question is, if voltmeter reading is equal to 2 volt, then V in is equal to how much? And the answer is simple. We know that this voltage drop VB is approximately 0.7 volt. Okay, it doesn't, I mean, this voltage is, it changes very small here. It may be around 0.6, 0.9, 7.1, but very close to 0.7. It can be 0.69 or 0.71 maybe, but very close to 0.7. So approximately, so it's a good estimation to say that V in is equal to 2 plus 0.7 volt. It's an acceptable approximation that we do. Okay. Now let's ask next question. What is the input impedance of this circuit. Okay, and let me also give you some numbers, like say Rm is equal to, let us take it 1 kilo ohm, okay, and beta is given as 100, okay, or let me take 99, okay. And so what is the input impedance? What is the input impedance of the measuring circuit when V in is equal to this 2.7 volt. Okay. So, which is my measuring instrument? Please identify that clearly. This is my measuring instrument. Together with this voltmeter, transistor, this power supply. So, this power supply, although I have drawn symbolically, I actually have a power supply like this, a voltage source which gives me this voltage VCC. Okay. So, what is the input impedance? Answer. So, how do we find input impedance? Input impedance means voltage applied divided by current. If this current I am calling IB, base current, then input impedance is nothing but V in divided by IB. So, we have to find IB. What is the value of IB? How can we find the value of IB? Now, you see that I can write V in minus, so KVL here, V in minus 0.7, 0.7, then this drop, then minus this drop which is Rm, meter resistance multiplied by IE. This is equal to 0. From this we can write V in is 2.7 given minus 0.7 minus Rm, or let me take this on the right side. So, this will be Rm times IE. IE is how much? IB times 1 plus beta. So, from this I can write this is equal to 2 volt is equal to Rm 1 plus beta times IB. I will take IB on this side, okay, or fine, let me write IB here. So, from this what can I write? IB is equal to 2 by Rm 1 plus beta, and therefore, from this I can write the input impedance going from here to here. V in is 2.7 divided by 2. Okay, let me first put this value. This is 2 divided by Rm is 1 kilo ohm, 1 kilo ohm, and this is 1 plus 99 is 100. So, this is 100 kilo. Okay. So, 2 by 100 kilo. So, 2 by 100 kilo above, and then this value is 100 kilo times, even if you approximate this as 1, this is slightly greater than 1. So, this is, I do not have a calculator, but I can write this is greater than 100 kilo. Okay. So, you see that the input impedance is greater than 100 kilo ohm. Let me just write, okay, I can write the exact value, why not? It is not difficult. This is this will be equal to 1.358 into 0 0, so 135 kilo ohm. Okay, that will be the resistance. Okay, so this is the answer. So what will be the meter reading if V in is equal to say 5.4 volt in the previous circuit here. Okay. So, if this is 5.4, what will be the meter reading? Simple, 5.4 minus 0.7. Simple, answer is 5.4 minus 0.7, this will be 4.7 volt. So, you observe one fact which is this. So, V in, if I make a table versus reading. So, for V in equal to 2.7, meter reading was 2 volt, and this for 5.4, the meter reading is 4.7. This is double. 2.7 times 2 is 5.4, but this is not double. So, you see, if I draw a curve, V in versus reading. So, at 2.7, this is 2, and at 5.4, this is higher, 4.7. So, if you join these different plots, you will get a straight line like this. This point will be 0.7. If you give a 0.7 input, then the out reading will be 0, because 0.7 minus 0.7, nothing will possibly remain theoretically. So, this you see is a straight line not passing through the origin. So, we say that the input output relationship is not proportional or not linear. It's straight line, but not passing through the origin, that is why we call it non-linear. So, this is a bad thing, this is a bad thing about this circuit. Okay. So, okay, let us take another example. I mean, let us continue this question. So, what is the input impedance when V in is equal to 5.4 volt? Okay. So, for this case, what is the input impedance? This is the question, and the answer, let us find it out. Okay, let me draw this circuit once again, or you draw it together with me for ready reference. So, we have voltmeter which is following this emitter, this always follows this voltage is always following this emitter, base collector VCC. This should be a high enough voltage to supply the extra current demanded by this voltmeter. Here I have 5.4 volt, okay, with respect to the ground, 0 volt. This drop is 0.7. Okay, so input, let us first find IB. How much is IB? Very quickly, IB will be, okay, I can first write IB into beta plus 1. This is same as IE, this current here. This will be given by 5.4 minus 0.7 divided by RM. 5.4 minus 0.7 divided by RM, which will be 4.7 by 1K. Okay. And from this input impedance, this will be 5.4 input voltage divided by IB. I am not writing the units, please forgive me for this imprecision. This is not right to do, I know I should not do it, but anyway I am doing it. Please do not do it in the exam. I am not writing the units, plus but you please do not do it. Okay. So 5.4 divided by IB, which is same as 5.4 by 4.7 into 1K. Sorry, this is IE. So IB is, so from this IB will be, you have to divide by this, which is 99 plus 100. So IB will be 4.7 divided by 100 kilo, which means like 4.7 volt divided by 100 kilo ohm. So that is so here 4.7 into 100 kilo, so that will be in ohm. Please forgive me for not writing the units properly. Okay. So this will be something which you can calculate, but this will not be same as the input impedance which we got previously here. Okay. It will depend. So it also depends. So you see, it depends on V in. So input impedance is not constant, but anyway this is a high number. It depends on V in, but it is very high, and it is higher than, much higher than the impedance of the voltmeter. That was RM 1 kilo ohm, but with this arrangement we are getting nearly, I mean more than 100 kilo ohm, right. So we are getting much higher than 100 times higher than the actual meter resistance with this arrangement. So that is the nice thing, that is the beauty of this circuit, but this is the deficiency of this circuit. The input output relationship is not linear. Okay. So we can see a new circuit, a modified emitter follower circuit. This is also called a practical emitter follower circuit. To make input output relation linear or proportional. Okay. So this is called a practical emitter follower circuit. Let me just first draw the circuit and you will realize the beauty yourselves. I will take two BJTs, one here and I will take the voltmeter. Okay, I will start from the previous circuit and then you see how I modify it. Okay. So this is the previous circuit, and here you apply V in. The beauty of the circuit is that here the current that will flow is IB, right, but the current that will flow here is more. Okay. Now I can do this, instead of connecting this voltmeter like this, I will connect the voltmeter like this. I will put a resistance here and the voltmeter here. So these are in parallel, they are in parallel, right. So now what will happen, this is equivalent to the previous circuit. why? The current that will flow through this, call it Im, through this voltmeter, it is given by this voltage divided by meter resistance. If this is Rm, so I can write this is equal to V in minus 0.7 divided by Rm. And even when I had the meter here, okay, in the previous circuit, in this previous circuit also, here also, sorry, not this one, and here, okay. So here also, the meter current is given by V in minus 0.7 divided by Rm. So if I connect the voltmeter like this way, then also this meter gets same current. So its reading will be same. Okay. So for same input, if I think about the input output characteristic, then if I put the voltmeter here or here, the input output characteristic is not going to change. Okay. Because this is the relationship between the meter current and the input voltage, or I can also write meter voltage Vm. So Vm is this plus minus, I can write Vm is equal to V in minus 0.7, and this relationship input output, meter voltage or meter reading and input voltage, this relationship is same no matter whether I connect it here or I connect it here, no problem, right? So this circuit is same as before. Okay. Now I will apply some modification, and this modification I will apply with a different color. On this side, I will, so previously it was grounded, at zero potential. Now I will make a modification and I will apply a voltage which is minus 0.7 volt, or better I will write it, this is equal to minus VBE. This is VBE, this drop, this can be 0.7, can be 0.69, 0.71, whatever is that value, I will apply the same voltage here. Okay. So I know this value, I can know this value, say I can know this value, then the same value negative of that, if this voltage drop is 0.7 volt, then I shall apply minus 0.7 volt here. If this is 0.6 volt, I shall apply minus 0.6 volt. If this is 0.8 volt, I shall apply minus 0.8 volt here with a battery. Think I'll do that. If I do this, then this equation will get modified like this. So what will be the meter voltage? Voltage across the meter. This will be, let me call this point A and this point B. Okay. Then I can write Vm is equal to Va minus Vb. Okay. And then I can write this as Va is how much? Va is V in minus this drop, VBE. I write A here, VBE is the drop, and I take the drop in this way, plus and minus. This is my reference. Okay. So I can write VA is nothing but V in minus VBE. Okay. And VB is how much? In place of VBE, I write minus VB. So this minus minus becomes plus, and then plus VB and minus VB cancels. I have only V in. Simple, right? I mean, there was a 0.7 volt drop here. If I can just compensate this drop by applying the same voltage on the other side, then the voltage across the meter will be same as V in. That's the idea. Okay, so this is the idea. Now there is a big question. The question is, big question, how do I apply minus VBE at point B? So at this point, how do I apply this? Okay, and I mean, in fact, do I know the value of VB precisely? I know it is around 0.7 volt, but could it be 0.71, 0.69? Then to be precise, I should apply that value only, to be more precise, to be more accurate, not 0.7. If it is 0.71, I should apply 0.71. If it is 0.69, I should apply 0.69. So can I have a provision so that I can easily figure out what this voltage is and apply the same voltage here? Okay, so can I figure out the exact value of VB and apply it easily, experimentally, practically, when using the meter? Can I do it? So that we shall see now. What I will do is this. I will take another circuit like this. Okay, another circuit like this to generate the required voltage here, which will be also controllable and adjustable. If I want to change it, I can change it. That's the beauty. So let's take so this circuit has generated here a voltage of minus 0.7 volt. So I need to generate minus 0.7 volt here. So I will take a similar circuit. So what I can do is this. I will let me take this color. So I will take this RE, same circuit I am drawing. This is a mirror image of this. I actually forgot one important thing here. This power supply. Sorry for that. Here also. So VCC. So you see this circuit and this circuit is same, identical, and therefore say if I now apply 0 volt, if I apply 0 volt and if these two transistors are identical, then the voltage at this point, this will be minus VBE. If this is 0 volt, then there will be a drop of 0.7 volt. So this will be at minus 0.7 volt. And now I can connect this. If this transistor is identical to this transistor, I apply 0 volt here, so I automatically get minus 0.7 volt, and then I can connect here. So here I have the voltage point minus 0.7 volt or minus VBE. So therefore, the voltage across the meter will be how much? Let me write it once again. Vm is same as Va minus Vb, this minus this, and Va is nothing but Vin minus Vbe, and Vb is nothing but minus Vbe. So this and this will cancel. I will remain with V in only. Okay. Now you should ask, what if these two transistors are not identical? What if, call it Q1, Q2, Q1 and Q2 are not identical? Okay. So for maybe this drop for this transistor is 0.7 volt, but here maybe this drop is 0.71. Let me write, I will just erase. So this is equal to 0.7 volt, this drop. So that means this point is at minus 0.7 volt, but maybe this drop is 0.71. So then this point is at minus 0.71. The easy solution is that in that case just apply a bit more voltage here, apply 0.1 volt at the base. So 0.1 minus 0.71 will give me 0.7 only. Fine. So that means I can change the base voltage. So I need a provision to change the base voltage. I'll erase this. And what I will do is this, I will take a long potential divider, give VCC here, give some minus voltage here V. This point you can vary. Normally you keep it around 0 volt. Normally you keep it around 0 volt. And if you require, you can move it up and keep it at 0.1 volt or maybe at minus 0.1 volt. This point you can vary. Okay. But how do you know exactly where to bring it? That you will know only if you know the value of VBE for this transistor and VBE for this transistor precisely. Then you can compute where to put it. Okay. So, but the fact is that we do not know the value of VBE, call it VBE 1 and call it VBE 2. VBE is the drop for this transistor, this is the drop for this transistor. VBE 1 and VBE 2 precisely. So what we will do is this, we will not try to find out the value of VBE 1 or VBE 2. We do not need it, we do not need it at all. What we will do is this. So before we start our measurement, so steps for measurement. Step number 1, make V in equal to 0. So you can connect it to the ground. Okay. So make this voltage equal to 0. So if you do that, this will imply that VA, this will be at, this is 0, so this will be at minus VB1. Whatever is the value of VBE1, I do not know. Now adjust this jockey J, jockey. adjust jockey so that Vm, which means the meter reading, is equal to 0 volt. So you move it up or down, whatever you like or whatever you need, so that the meter says 0 volt, right? If you do so, then this will imply what? Vm equal to 0, this means Va is equal to Vb. Okay. So Va is equal to Vb, so this will imply Vb is now set to the value of Va. Now, but Va is Vb. Please understand each statement carefully and then proceed. Okay, because I have set Vm equal to 0, this means Va is at minus Ve, and therefore if I adjust Vm to be 0, that means Va and Vb same, then Vb must also be the same at the same value as Va, right? So it will automatically be Vb 1, and this will also imply that this voltage, call it Vb2, this will imply Vb2 is equal to how much? This voltage minus Vbe1 plus this drop, okay, plus Vbe2. We always take the drop from base to emitter as the positive by convention, or I can write it for you. Vb, let me write it by erasing this. Vbe2 is between this and this side positive, this side negative. Okay, so this will automatically happen. I mean, if you let me tell you even simply. So I mean, the idea is whatever is the error or wrong, I mean, Vb drop here, you want to get it compensated by generating the same value on the other side, and for that you make it 0. So this is minus Vbe1, and then you adjust it until and unless this is also equal to Vbe1, and then you can make it sure by checking that these two are at same potential, so that the meter reading is 0. Okay. Now, once this is done, then step 2, remove this short circuit and apply unknown voltage at Vin. Okay. So that's the idea. So let me just summarize in 2 minutes these things. Okay. So this is my primary circuit. Emitter follower circuit. I have the voltmeter here. If I apply a voltage V in here, I know the voltage that will come at this point, call it A. At this point, VA is equal to V in minus VBE1, VBE1. Okay, this is what I know. This will always happen. This I connect here, and therefore I want to get this same value on the other side. For that, I just take a similar circuit. I don't need this to be exactly same, it doesn't come in the theory at all. So this may not be exactly equal, fine. These two transistors also need not be exactly equal. And what I do, call this VB2, this point is B, minus V, so it can vary between these two. Okay, so adjust jockey, this jockey, adjust jockey to make this voltage. This is point B, so you call this VB. Adjust jockey to make VB is equal to this voltage VA not VA is equal to minus VB1, which is same as the value of VA when V in is 0, and we are done. So essentially I needed to correct for this voltage by applying same voltage on the other side. Okay, same voltage I want to apply on the other side, and I do it by experimentally changing and finding what is the position of this jockey, which gives 0 voltage across the meter. This is how to use it. Okay. Okay, so that's it about this topic. Okay, I will just ask. I'll just point out two facts. So facts are: what is the voltage gain of this circuit? Voltage gain means this will be the meter voltage. Why are we talking about voltage gain? Because we know that in an electronic voltmeter, one of the purpose is to amplify a small voltage so that it becomes easier to measure. Another purpose is to increase the input impedance. These are the two important purposes, right? So let's check whether those purposes are satisfied. So let's check if there is a gain in voltage. So voltage gain will be the meter voltage, the voltage that appears across the meter, divided by the input voltage V in. But you see in this circuit this is equal to 1. Why? Because this point is at this voltage V in minus VB1. We have also adjusted to make this equal to VB1. Adjusted. So this is VB1 and this is this. Now what is the difference? The difference is just V in. Okay, because meter voltage is same as V in. So V in by V in, this is equal to 1. So no gain. So this circuit doesn't amplify a small voltage at all. Okay, which is one of the requirement of a electronic voltmeter. It doesn't do it, but that's fine. It serves the other purpose. Okay, the input impedance. How much is the input impedance? This is very high. Why? Because input impedance is nothing but I can write. So I will connect some circuit here. V in plus minus. Okay. So if this current is IB1, then the input impedance is nothing but V in, the voltage applied divided by the current IB1, and this is very high. Okay. Since this is low, since normally base current is low for a transistor, is low. And more importantly, the current that will flow through the meter, majority of it comes from this power supply. if IB1 amount of current is flowing through this, then beta times IB1 can be drawn from this part. Okay, IB1, okay, part of it goes through this, part of it may go through the voltmeter. So if only a small amount of current is drawn from here, a large amount of current can be supplied by this, which will partly go through this and partly go through the meter. So the meter current can be larger than this. Okay, so input impedance is very high. So this circuit is an electronic voltmeter which serves one of the purpose of having high input impedance, but it doesn't serve the purpose of voltage amplification. Okay, so thank you.